This is SpaceTime, Series 25, Episode 84. Coming up on SpaceTime, new studies suggest you'll need to dig deep if you hope to find life on Mars. The Mars helicopter grounded by a sensor glitch, and the launch of a new joint American and Australian spy satellite. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has confirmed that future Mars rovers will need to drill at least 2 meters below the red planet's surface in order to find any evidence of ancient Martian life, if it ever existed there. The recommendations follow experiments designed to determine how far below the ground the effects of ionizing radiation from space can penetrate under Martian conditions. Ionizing radiation degrades small molecules such as amino acids relatively quickly. Amino acids can be created by life and by non-biological chemistry. However, finding certain amino acids on Mars would be considered a potential sign of ancient Martian life, because they're widely used by terrestrial life as a component for building proteins, and proteins are essential for life. They're used to make enzymes that speed up or regulate chemical reactions and to make structures. The study's lead author, Alexander Pavlov from NASA's Goddard Space Flight Center in Greenbelt, Maryland, says tests suggest that amino acids are destroyed by cosmic rays in the Martian surface rocks and regolith at much faster rates than previously thought. The thing is, current Martian rover missions, such as Curiosity and Perseverance, only drill down to depths of about 5 centimeters. At those depths, it would only take about 20 million years, short in geological time, to completely destroy amino acids. And the addition of perchlorates and water further increases the rate of amino acid destruction. Now, a period of 20 million years is considered relatively brief because scientists are looking for evidence of ancient Martian life on the surface that would have been present billions of years ago, a time when Mars was much more Earth-like. The findings, reported in the journal Astrobiology, suggest a new search strategy for missions that are limited to sampling in shallow depths. It recommends that Curiosity and Perseverance have to seek recently exposed outcrops, such as recent microcraters with ages less than 10 million years, or material that's been ejected from those craters. Cosmic rays are high-energy particles, mostly protons and helium ions. They're generated by powerful events in the sun and from deep space, such as solar flares and exploding stars. They can degrade or destroy organic molecules after penetrating even meters into solid rock, ionizing and destroying everything in their path. Luckily, Earth's thick atmosphere and global magnetic field help shield the planet's surface from most cosmic rays. And in its youth, Mars also enjoyed a global magnetic field with a thick atmosphere. Evidence shows that Mars was once a warm, wet world with streams, lakes, and an ocean billions of years ago. Since liquid water is essential for life as we know it, scientists want to know if life ever emerged on Mars, and they can search for evidence of ancient Martian life by examining Martian rocks for organic molecules such as amino acids. Problem is, Mars is a lot smaller than the Earth, so it cooled far more quickly. And as its core solidified, the geodynamo process, which generates a planet-wide magnetic field, also faded away. And without a protective magnetic field to shield the atmosphere from the solar wind and cosmic rays, it was gradually eroded away, turning Mars into the freeze-dried desert it is today. Pavlov and colleagues mixed several different types of amino acids in silica, hydrated silica, or silica with perchlorates in order to simulate conditions in Martian soil. And they then sealed their samples in test tubes under vacuum conditions to simulate the thin Martian atmosphere. Some samples were kept at room temperature, about the warmest it ever gets on the surface of Mars, while others were chilled down to a more typical Martian temperature of minus 55 degrees Celsius. The samples were then blasted with various levels of gamma radiation in order to simulate cosmic ray doses up to that received from about 80 million years worth of exposure in Martian surface rocks. The experiment's the first to mix amino acids with simulated Martian soil. Previous experiments tested gamma radiation on pure amino acid samples, but it's highly unlikely to find a large cluster of a single amino acid in a billion-year-old rock. The authors found that the addition of silicates, and especially silicates with perchlorates, greatly increases the destruction rate of the amino acids. While amino acids haven't been found on Mars yet, they have been discovered in Martian meteorites. Pavlov says he's identified several straight, clean amino acids in the Antarctic Martian meteorite RBT-04262, which was examined at the astrobiology lab at the Goddard Space Flight Center. He believes the amino acids originated on Mars and weren't contaminated by Earth biology. Organic matter has been found on Mars by both NASA's Curiosity and Perseverance rovers. However, it's not a conclusive sign of life, since it could have been created by non-biological chemistry. Also, there's a regular cyclic change in methane levels in the Martian atmosphere. Again, it could be biological, but it's also just as likely to be non-biological chemistry. The experiment's results also imply that it's likely that all organic material observed by the rovers on Mars has been altered by radiation and therefore is not as it was formed. This is SpaceTime. Still to come, NASA's Mars Ingenuity helicopter grounded because of a sensor glitch, and a new joint American and Australian spy satellite launched from New Zealand. All that and more still to come on SpaceTime. NASA's Mars Ingenuity helicopter is being grounded after suffering a sensor failure. The problem is in Ingenuity's inclinometer, which is needed to orient the helicopter prior to lifting off. The inclinometer consists of two accelerometers whose sole purpose is to measure gravity prior to spin-up and takeoff. The direction of the sensed gravity is used to determine how Ingenuity is oriented relative to the downward direction. Without the sensor working, mission managers are keeping the tiny tissue box-sized rotocopter on the ground, at least until a computer patch providing a workaround can be uploaded. The 1.8 kilogram chopper arrived on the red planet's Jezero crater attached to the Perseverance rover back in February last year. It was only ever meant to test the ability of a small drone-like aircraft to fly on an alien world, undertaking maybe 5 or so test flights. But Ingenuity has continued to operate successfully, undertaking 29 missions so far. That's significantly more than originally planned. Most in support of Perseverance, scouting ahead of the rover to find interesting geology and surveying the landscape around Perseverance to help plot its course. However, the tiny chopper was never designed to operate in the harsh environment of the Martian winter, and this has posed significant challenges. See, because it wasn't expected to last this long, measures weren't taken to ensure that it could get enough power from the sun during the short Martian winter days. And so it needs to be completely shut down at night, which leaves it exposed to temperatures as low as minus 80 degrees Celsius. And those sort of temperatures can damage its delicate electronics. And then there's the constant shift in temperature extremes, which can also cause real damage to circuits. Finally, along with everything else sent to Mars from Earth, dust is a real problem, especially in the winter. The good news is the software patch has been designed to work around the damaged sensor, and it just needs to be uploaded and tested to get the chopper back in the air. We'll keep you informed. This is SpaceTime. Still to come. A new joint American and Australian spy satellite launched from New Zealand, and later in the science report, rare sauropod dinosaur teeth discovered in outback Queensland. All that and more still to come on SpaceTime. Rocket Lab have successfully launched the first of 2 new spy satellites for the Australian and United States governments. The highly classified NROL-162 spacecraft mission, which is being jointly operated by the United States National Reconnaissance Office and the Australian Department of Defence, was flown into orbit aboard an Electron rocket launched from Complex 1A on the southern tip of the Mahia Peninsula on the east coast of New Zealand's North Island.
Today's mission will be the third NRO mission to fly on Electron under the Razor contract, which supports the NRO to launch small satellites commercially through a streamlined approach.
For every launch to space, we come up with a name that represents that particular launch and our customer's mission, and a unique mission patch to match. For NRO L162, the name Wise One Looks Ahead is a translation of the NRO's Latin catchphrase for this mission, Sapiens Qui Prospicit. For the NRO, this represents their work with present and future partners in space. In particular, it's a shout-out to their partnership with the Australian Department of Defence, as the NRO commits to enhancing its relationships with allies.
And while the bird on the patch might seem familiar to our US viewers, it is in fact an Australian wedge-tailed eagle, used on this patch to further symbolize the two organizations' partnership in space. The NRO has also come up with its own patch for this mission, one which instead features an Australian frilled neck lizard to represent the small and agile nature of the payload being launched on today's mission.
All operators, this is the LD on mission, proceeding with the go, no-go sequence. Stage.
Stage is go.
Avionics.
Avionics is go.
VCON.
VCON is go.
T1.
Let's go.
GC.
GC is go for launch.
PLS.
PLS is go.
RSO.
RSO is go.
MET.
MIT is go.
GNC.
GNC is go.
MM.
MM is go.
SVMD.
MD is go.
LD SUP.
LD SUP is go.
That completes the go, no-go sequence. We are go for terminal count at T-minus 10 minutes. From this time, the three-word hold procedure is in effect. This is the LD on mission. From now on, there should be no red flags on your critical LCCs. VCON LD on mission.
LD VCON.
Yes, sir. Please confirm all expected flight computer as-goes are green.
Confirmed. All as-goes are green.
And VCON lock auto sequence and confirm.
Confirmed. Auto sequence is locked.
This is the LD on mission. We are go for auto sequence start at T-minus 2 minutes. LD is go for launch.
LDGC on mission.
Go ahead, GC.
ECS disabled, pad auto sequence is armed, pad ready for launch.
Copy, GC.
Vehicle is on internal power. AFDS is green and enabled for flight.
Lock load complete. Lock system in recirc. All helium anti-gathering disabled.
Stage 1, Stage 2, press for flight.
High flow engine purge enabled, water deluge activated.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And we have liftoff.
Vehicle is clear.
Stage 1 propulsion is nominal.
High voltage battery discharge, nominal.
Our 28th Electron launch vehicle has successfully lifted off the pad and is on its way to space. Before it gets there, it has a number of critical milestones to pass through. The first of which is called Max Q. Max Q is the first test in Electron's journey, where it experiences maximum aerodynamic pressure, or where the forces on the rocket are at their peak.
Past Max Q.
There's the call. Mission Control has reported Electron has successfully passed through Max Q, its first milestone after lifting off from the east coast of New Zealand. The 9 Rutherford engines on Electron's first stage are performing well, and we're ready for the next series of milestones in the launch process.
Up next is main engine cutoff, known as MECO, which immediately precedes Stage 1 separation. MECO allows the vehicle to decelerate slightly before the first stage separates from the second stage. As the first stage falls back to Earth, the single space-optimized Rutherford engine on the second stage ignites to take the vehicle, with payload, the rest of the way into space.
Stage 1 propulsion holding nominal. Standby for MECO in around 30 seconds.
High voltage battery discharge, nominal. Entered burnout detect mode.
MECO confirmed.
Stage separation successful.
And stage ignition.
Electron's first and second stages have successfully separated. The single space-optimized Rutherford engine on Electron's second stage is glowing red as the nozzle radiates heat from the exhaust. Because the vehicle has now cleared the majority of Earth's atmosphere, we can get rid of the payload fairing to shed some extra weight.
Fairing jettison succeeded.
Stage 2 propulsion is
And there it
nominal.
is. You can hear the payload fairing tumbling away on your screens now. The NRO payload is now exposed to space in preparation for payload deployment later in the mission.
This fairing will burn up as it re-enters the atmosphere, while the second stage continues on. The vehicle cleared Pad A at Launch Complex 1 at 0630 UTC and has successfully passed through its initial key milestones on its way to payload deployment. The second stage is now ignited and carrying the kick stage with the payload attached the rest of the way into space. At about 10 minutes into the mission, the kick stage will separate and its Curie engine will precisely deliver the payload to its intended orbit.
The shape of an orbit is important. In fact, the entire capstone mission we launched last month is to test the efficiency of the near rectilinear halo orbit, or NRHO, around the Moon. In most Electron missions, our second stage delivers the payload to an elliptical orbit. We then use the Curie engine on the kick stage to circularize that orbit, basically make it circular, to deliver the payload to its new home in space. Quick update, Mission Control is reporting the vehicle is healthy and making good progress onward to deliver its NRO payload.
If you were ever curious, when Electron takes off, it weighs 13 tons, but 90% of that is actually fuel. Electron is so efficient that by the time we reach MECO, it only weighs 1.25 tons. To optimize our weight, we also use a carbon composite shell that in some places is less than 2 millimeters thick. That's thinner than your windows at home. Carbon fiber materials are strong enough to manage the environmental stress from launch while being lighter weight than traditional materials, so we can bring even more payload mass to space for the same fuel.
Electron is one of a kind for many reasons, and one is that its engines, all 11 of them, use electric pumps to feed the propellant. Batteries are one of the few items that maintain their weight as they are drained, so once we use them up, we need to get rid of them to keep our flight easy and efficient. This process is called the battery hot swap, and is about to take place as the batteries we started with at liftoff are now depleted.
Hot swap successful.
There you have it. It happens quick. Electron continues nominally through its second stage burn, with kick stage separation coming up in the next few minutes.
AFDS has saved.
The vehicle is continuing well onto orbit, and we're making good progress in our journey to payload deployment. Before, you may have heard Katie talking about how much of the mass of a space rocket is propellant or fuel. But what happens as we use it up? Electron uses most of that fuel in just 8 minutes, which creates a lot of empty space inside the rocket. We actually use helium gas to maintain equilibrium in pressure between the inside and outside of the rocket.
High voltage battery discharge holding nominal.
The Rutherford engine on our first stage inspired this second stage, but they operate in fundamentally different environments. Rutherford nozzles are designed with a focus on corrosion resistance and environmental robustness, as it must survive the super high temperatures and pressures during launch. Our second stage engines are designed for space propulsion, so we instead focus on making sure it can cool itself off as it gets extremely hot without convection in the vacuum of space. Both of these engines are 3D printed in our Rocket Lab factory in California, allowing our engineers to easily make small tweaks to make our engines more and more efficient after each flight.
Entered burnout detect mode.
Stage 2 propulsion.
Our next big milestone for Electron is second engine cutoff, or SECO. Just like MECO, or main engine cutoff, the engine on this stage will shut off ahead of the final separation of the second stage from the last or third stage of the vehicle, the kick stage. At this point, the small but mighty Curie engine on the kick stage will carry the payload to its exact destination in space.
SECO confirmed.
Perfect transfer orbit.
Nominal transfer orbit achieved. Stage 3 separation confirmed.
We've received confirmation from Mission Control that Electron's second stage engine has shut down and the kick stage has successfully separated, now en route to deliver the payload to its destination in orbit. Over the next hour or so, the kick stage will make its way to the correct location in low Earth orbit ahead of payload deployment.
The mission, known as the Wise One Looks Ahead, will be followed next week by a second mission called Antipodean Adventure, which will lift off from the adjacent Launch Complex 1B, carrying the NROL-199 spacecraft for Washington and Canberra. No details of the spacecraft's mass, payloads, missions, or even their final orbits have been released. Meanwhile, China's also been busy launching another 2 Earth observation satellites designed to keep an eye on areas of interest. The Siwi Gaojing 201 and 202, or SuperView Neo 201 and 202, were launched aboard a Long March 2C rocket from the Taiyuan Satellite Launch Center in Jiangxi Province. Beijing are planning a constellation of at least 28 of these SuperView satellites, which will come in 3 different configurations. The SuperView 1 satellites will provide high-resolution coverage down to just 20 to 30 centimeters. The SuperView 2 satellites will feature synthetic aperture radars for day-night all-weather operation with a resolution down to half a meter. The final batch of satellites, the SuperView 3s, will perform wide-area optical imagery with resolutions of better than a meter. Beijing describes these spacecraft as being intended for commercial remote sensing services, for land resource investigation, natural disaster monitoring, urban planning, agricultural crop monitoring, and for public safety. However, their primary use will be by the Chinese military for surveillance and reconnaissance operations, providing near-continuous high-resolution electronic monitoring of areas of interest to Beijing as part of Xi Jinping and the Communist government's preparations for war. Less than a week before the SuperView launch, China launched its third Tailian-2 Sirius space telecommunications relay satellite aboard a Long March 3B rocket from the Xichang Satellite Launch Center in southwestern China's Sichuan province. The new second-generation Tailian 203 satellite was placed into a geostationary orbit, where it will join its two sister satellites in relaying commands to other spacecraft, providing improved control, tracking, and data relay capabilities. The Tianlian family also serve as rendezvous and docking ports between spacecraft and space stations. They provide video links, and they can even transmit data, both about their observations of the Earth below and, importantly, of the location of other satellites. Following these latest launches, China now has an estimated 512 satellites orbiting the Earth. Since 2016, Beijing has launched more than 194 Earth observation satellites. This is SpaceTime. And that's the show for now. SpaceTime is available every Monday, Wednesday, and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from SpaceTimeWithStuartGarry.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGarry.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to SpaceTimeWithStuartGarry.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGarry on Twitter, @SpaceTimeWithStuartGarry on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.